Hello everyone, welcome back to our NEET live lecture series, Your Power Hour for your NEET 2025. And in today's class, we have brought you another important topic of physics optics. Alright, so without wasting any time further, we are going to start with hand-picked problems of your optics, the symmetrical optics and the wave optics, and we are going to brush up the important concepts required for those questions. Alright. Now, before before going on to the questions, let's discuss a little bit about what topics in optics are there, or let's say what topics will be handy if we are going to solve the questions. So, firstly, if you know, in your reflection through plane surface, we have just the concepts that the length of mirror required to see the complete image of a person, the minimum length is going to be L by 2, such concepts. But in the curved mirrors or spherical mirrors, you have the mirror formula. What's the mirror formula? Mirror formula is the relationship between the object distance and the image distance. One upon u, 1 upon v equals 1 upon f. Now, if I have got the image formula and the object distance, then I need to check the magnification. So your magnification is height of image upon the height of object, which comes out to be minus v upon u. In this, you can look for the longitudinal magnification also. This is the transverse magnification. Longitudinal magnification deals with the length of the object. I can write it as delta V upon the length of the image. I can write it as delta U. Now, for the length of the object, you need to write let's say an object is nothing but the composition of different points, out of which I'll check the starting point and the end point. So I can write this as V2 minus V1 upon U2 minus U1. Then comes the concept of reflection and the refraction through plane surfaces. I know that whenever we talk about refraction, there is a little bit of reflection involved. It's always involved, okay? But in the optics, we are going to purely focus on the refraction part. In the wave optics, we discuss both, okay? All right. So in the refraction, we talk about refraction through plane surfaces. In that refraction, I know कि first law of refraction is your Snell's law. The another law is same as the reflection law. The incident ray, refracted ray and the normal, they all lie in the same plane, like that. Snell's law is pretty important. Sin I upon sin r, mu2 upon mu1. Now basically remember that if there is a refraction going on through multiple layers or multiple surfaces, let's suppose like this, the light ray passes through one medium, enters another medium, and then it goes to another medium further. So let's suppose the first medium refractive index was mu1, second medium refractive index was mu2, third medium, and so on furthermore refractive indices. In the first medium, angle of incidence is suppose theta 1. Okay, and in the second medium, angle of refraction is suppose theta 2. Thus, the angle of incidence again for the next boundary is going to be theta 2. And furthermore, the angle of refraction in the next medium will be theta 3. So, what do we write? Whichever medium and the angle in that medium, whichever medium mu2 and the angle in that medium. So, the product of refractive index of that medium and sine of angle theta in that medium remains constant. Sine theta 3. So in this Snell's law, if you just cross multiply sine I, angle of incidence for the first medium, so mu1 gets multiplied with sine I, sine R, angle of refraction in the second medium, so mu2 gets multiplied with sine R, and so on. Okay, so this was refraction through plane surface. Then comes your refraction through curved surfaces. These are just the outlines of all the topics we will see. There are many formulas which you need to revise. Curved surface. So in refraction through curved surface, we need to see the image formation, angle of incidence and the angle of refraction formula. So suppose there is this boundary which kind of separates two optical media, the mu1 medium and the mu2 medium. There is an object placed in the medium 1, and I can say its distance from the pole of this boundary or the origin of this boundary. I can say this point reference as the object distance. Wherever the image is formed, maybe here or maybe somewhere else, I'll call this as object and this as image, so the distance V. Now this distance I have shown in the diagram, but again these distances I am going to take with proper sign convention. What's the formula? This is the initial medium, this is the final. So we write mu2 upon V minus mu1 upon U equals mu2 minus mu1 upon the radius of curvature of the boundary. This is the boundary. Here again remember that we need to keep everything with proper signs. What are the signs? We say that if this is the object and this is the boundary, then incident ray will be this. So if you have chosen the incident ray, then the distance is measured in the direction of incident ray from this pole of the boundary will be taken positive, while the distance is starting from this pole. Okay, the boundary basically will be negative if they are opposite to the incident ray. Next one is the formula of lenses, the lens formula. So lens formula is straightforward. In the lens formula, whatever knowledge you have about the spherical mirrors, whatever formulas you remember from the spherical mirrors, just replace a little thing in all of those formulas. I am going back to just give you an overview that these were the formulas, correct or not, for spherical mirrors, curved mirrors. So wherever you see U, this object distance U, wherever you see U, you just replace it with minus of U and you get all the lens formulas. So 1 by V as it is, but instead of 1 by U, I write minus 1 by U. 1 upon F. Magnification is HI upon HO. It was minus V by U, so minus V upon minus U will be V by U plus V by U. Then we can convert it to the other formats of focal length also. Like it was F minus V upon F, so here no change, and the other one of F upon F minus U, which then becomes F plus U for the lenses. Okay, the magnification formula. Okay, so this was about the lenses, the mirrors, the plane surface and the curved surface refraction. Now the thing is key in this we see magnification as well as optical power. Optical power for mirrors and for lenses. Okay. For the mirrors, the optical power measured in diopter is represented as minus 1 upon focal length if it is in meters. If it is in centimeters, convert it to first meters and then you will get the answer. This power should come in diopters. Diopters. For the lenses, the formula is same, just the sign again. Here we take the negative sign and here we take the positive sign. Again it should be in meters then we'll get the answer in diopters. Diopters. So this was your formula of power. Optical power basically implies converging power of that device. Why converging power? In simple words, if I say, suppose there is a lens and incident ray is falling onto it parallel to the principal axis, which is basically coming from very, very far away points. Now, you know that it's going to converge to the focus of this device, correct or not? Tell me, if the focal length is more, then will it converge nearby or is it converging far away points? It's going to converge far away. That means its converging power is less because it's not applying a lot of power in bending the rays towards the lens. That means its converging power is less. So I can say the power and focal length are inversely related, which we can see. More the focal length, lesser the converging power. Okay. Next up is your refraction through prisms. So the prism theory is again very important. It's very little but very important. Prism theory. What is in the prism theory? You need to know a few aspects about the prism. The angle of incidence, the angle of refraction, the another angle of refraction and the angle of emergence, and the relation between them and the angle of deviation. So many angles are there, but again we can do it. Okay. So this is our prism, let's say. We define one of the angles as angle of prism or apex angle. Angle of prism or apex angle. Prism angle or angle of refracting angle. Basically, it will be the angle between two refracting surfaces, any two refracting surfaces through which the light is going to suffer refraction. So let's say कि there is an incident light striking this prism on this side and it suffers a refraction at the first boundary like this, and then it moves further to the second boundary, again it suffers refraction and goes on like this. So basically it suffered two refractions, and in these two refractions I am going to mark the angles. First one is angle of incidence I, then this one is angle of refraction R1, then the next one is angle of refraction, let's write it here, R2, and the final angle in the, again in the air outside the prism will be emergence, angle of emergence E. Get it or not? So this is how we need to relate these angles. The first one you need to check is this. Angle of prism, the prism angle, angle of refraction R1 and angle of refraction R2. This is our first relation. Second relation is for the net angle of deviation. What is deviation? This is the incident ray. It was supposed to go in this direction, but I see that it's not doing that. It went in this direction, it turned little bit, then again it turned little bit more. So it suffered overall deviation. I'll say that is delta angle. It is equals to sum of angle of incidence plus angle of emergence minus the angle of prism. These two formulas I must know for the prism theory. Get it? Now, for the prism, if we talk about minimum deviation and thin prisms, so for the minimum deviation, the result will hold true for thin prisms also. For minimum deviation, I say that key angle R1 and R2 are going to be same. If R1 and R2 are same, then angle I and angle E will also be same. So from this relation you can easily write that if R1 R2 is same, then it is equals to A by 2. Okay? And I is equals to E. For this we will get the minimum deviation, and from here if I write delta minimum delta M is equals to 2I minus A. Now sometimes they are going to give you a few points, a few data regarding this thing. What they can give is, they will give you the minimum deviation for a particular prism. Get it or not? They can give you this angle of incidence, let's say ki whatever is the angle of incidence. They can give you angle of prism. Now tell me, can we figure out angle of incidence from here through these two things, and also angle of refraction from here? If I get the angle of incidence and the angle of refraction, cannot I apply Snell's law? Yes, we can definitely apply Snell's law. So if I apply Snell's law, I can write mu is equals to sine I upon sine R at one boundary. Okay, just the first boundary you can say here. Sine I, from here I can write it as delta m plus A divided by 2. So it is sine of delta minimum plus angle of prism divided by 2. I got the angle of incidence divided by R is A by 2 angle of refraction. This is how we can get the mu, the refractive index of the prism, using the concept of minimum deviation. Let's take another kind of figure. Okay. No, let's leave it. Alright, so this is our formula for the minimum deviation. Okay. This was about your prism. Now in this I said ki the similar kind of relation holds true for thin prisms. What is thin prisms? For thin prisms, the angle of prism A is quite small. It's lesser than kind of 5 degrees or max to max 10 degrees, but not greater than that. So if it is somewhere what lesser than 10 degrees or 5 degrees, I'll consider it as thin prisms. For thin prisms, angle A is small. How much small? It's lesser than kind of 10 degrees. So if angle A is small, my prism will be like this, very small. So whatever angle of deviation array will suffer, I'll consider it as small, so it will be minimum only. Okay. So all angles will be like this, so delta will be 2I minus A in general. Correct? Now tell me, if A is very small, won't the delta be also kind of very small? Correct. It will also be small. So all the angles will be small, and I can use the same formula. While here delta m will be small, A will be small, A will be small. So if you remember the small angle approximation, I can write sine theta approximately equals to theta in radians, obviously, for small angles. And then we can relate it with refractive index here. So sine of delta plus A by 2 will be simply delta plus A by 2 and divided by A by 2. 2 I have already cancelled, just cross multiply. So what I'll get, delta is equals to mu minus 1 into A. From this and this formula, I have gotten the formula of angle of deviation for thin prisms. Okay? It is definitely the minimum angle of deviation, and for thin prisms all the angles will be small enough. Okay. Fine. So from these things we are ready to do some problems of optics, the ray optics specifically, and then we'll take a few problems, 1 or 2 problems of wave optics as well, the important problems afterwards. Okay. So let's start. First problem is, in the figure shown they have given me 2 mirrors. So NEET definitely asks the problems of combination of optical devices like the lens and the mirror and the mirror, lens and the lens, obviously. First one is there is a convex mirror. Can you see that this surface is silvered? So this reflecting surface is convex. Here the rear surface is silvered, so the reflecting surface is concave. Focal length of convex is taken as positive 10 centimeters, while the focal length of concave is taken as negative. This we have to do on our own. They will just give you the values, not with the sign. Next they are asking, in the figure shown, the total magnification after two successive reflections, first through M2 and then through M1. For this you need to understand what is their perspective with these two reflections. First through M2 means I'll take up this object. This is the object. This is our object O. I'll take up this object. I'll make its image through M2. This one is M2 first, the concave one. I'll make the image through the concave one. I'll take that image wherever it is formed, whether it's on this side or on this side. It's definitely on this side only, okay, on the front of the mirror. So I'll take that thing as the intermediate image and it will act as object for the second one. Let's do it. Let's try to solve it and then you will get an idea of what I'm saying. Okay. Or I'll do one thing. Okay, here let's use this diagram. Great. Now see, what did I say? I'll use this mirror. First one, they said ki the reflection first on M2 and then on M1. So first one is M2, the concave. In this you need to be careful that in what direction the ray is going. It's going in this direction. Get it? So object distance is negative. If it's a real object, it has to be negative. I'll write the object distance as minus 30 centimeters. Focal length we have already written. It is minus 20 for the concave because its focus is on the front side. So find out the image distance. 1 upon V, 1 upon U, 1 upon F. Get it? So if you put U, it will be minus 30. V, I'll keep it here. Focal length is minus 20. So I kept it here. Take this minus 1 by 30 on the other side. So it will be minus 1 by 20. Minus becomes plus. Plus 1 by 30. Take LCM. What I'll get? Cross multiply. So LCM, if I take it as 60, then I'll put minus 3 and here I'll put 2. So it will be minus 1 by 60. Take the reciprocal. So I got your image distance as minus 60 centimeters. From this you need to be careful. What does it mean? It means that the image is in front of the mirror, same side. Okay. The two mirrors are placed at a gap of 40, yet the image through the first one is formed at 60. From here, from this point M2, it's formed at 60. That means, can I say that it is formed 20 centimeters behind your M1 mirror? Correct. I have got the location of the intermediate image, or I'll call it as I1. Okay, and it will act as object for this mirror. It will form the final image and I need to get the final image. Okay. So I'll write for the second refraction, sorry, we are talking about reflection. I'll again apply the formula. For that I am going to write the distances. Now please note key, how did I choose the distances? The image was formed here behind. The rays would be falling like this. That's why only the image is formed there. So these are the incident rays and we are measuring the distance in the same sense. So its object distance is positive this time, plus 20, as well as focal length is positive. Again it's plus 10. Tick. So let's put the formula. 1 by U, 1 by V is equals to 1 by F. U is 1 by 20. 1 by V, and then F is 1 by 10. Okay, take this on the other side. So V comes out to be, it will be 1 by 10 minus 1 by 20, that is 1 by 20 only. So V is plus 20. That means the final image is formed here itself on that point. Okay. If I check the problem, they are asking the magnification after 2 successive reflections. So now see here. The magnification of the second reflection, you can easily see it will be minus 1. Okay. Magnification of second reflection will be minus V by U. So it is minus 1, straightforward. Magnification of the first reflection M1 will be minus V upon U, and here the minus V was minus 60, so minus 60. Object distance was minus 30, so minus 30. Cancel it, so it becomes what? 2 minus 2. Here the magnification is minus 2, sorry, in the first one magnification is minus 2 and in the second one magnification is minus 1. You need to cross multiply both to get the total magnification in consecutive reflections. M1 into M2. If I multiply it, so minus 2 into minus 1 will be what? Plus 2. This is how you are going to answer the problems. Plus 2. Okay. This one here. Again, go through this problem. Just follow step by step process and you are going to get the answer very easily. Let's move on further to the next problem. Okay. Here I have a linear object which is placed on the axis of the mirror as shown. This is your mirror, okay, and this is a concave mirror like this. This is the mirror. They are saying ki if f is the focal length of the mirror, then the length of the image is, okay. For the length of the image, you just need to remember that I need to take this object as set of 2 points, the starting and the ending point, the A and the B. They are saying ki this point A is kept at 2f. So can I say this is the center of curvature? 2f is the distance magnitude wise. So yes, A is kept at the center of curvature. That means its image is going to form at the center of curvature itself. We know this thing. Now let's look at this point B. Now distance of point B from the pole, let's say ki this is the pole of this mirror, okay. From the pole is 3f by 2. What does this imply? It implies ki the object is between f and 2f. So its image will be formed beyond 2f, behind this, correct or not? So if I draw its image will be kind of formed here. Okay? Like this. So this will be your image of B, I'll call it B dash, and this will be the image of A, I'll call A dash. And we need to get the length of the image, that means this distance. B dash minus A dash or A dash minus B dash, magnitude wise length of the image. So here I can easily say if the length of the object was f by 2, correct or not? Okay. So we can figure out what will be the length of the image. Let's find the image distances for these 2 points. Firstly, for point A, get it? Object distance for point A is minus 2f. So if you write the formula properly, you will get image distance also minus 2f, which I know. Correct or not? We just drew it. For the point B, tell me, for the point B, if you can just get the image distance, your job is done. Subtract 2f and you get the length. So for point B, I'll write 1 by V is equals to 1 by f minus 1 by u. Focal length is, remember that, I have to keep here with sign. Everything has to be with sign when I use the mirror formula. So minus 1 by f, because f is the magnitude only. They did not say ki it is with the sign, f is the magnitude. The distance was 3f by 2. Put it with sign. So it will be minus 3f by 2. Take the LCM and everything. It will be minus 1 by f and plus 2 by 3f. So if you write it properly, take the LCM 3 and it will be minus 1 over 3f. So my image distance is minus 3f. Get it? So what I am seeing, the point B is at a distance of 3f magnitude wise. Point A dash was at a distance of 2f. So the length of the image, if I need to write length of the image A dash B dash will be the distance of B dash minus the distance of A dash, which will be 3f minus 2f. Magnitude wise I am talking because sign I already know. F. So the length of the image comes out to be f. Again, it's the length, magnitude wise only. Okay. Let's take another one. This time they are using a glass slab of thickness 3. For the glass slab, you must remember what's the formula of lateral shift or delta x. It is T times 1 minus 1 by mu. If you know the refractive index, if you know the thickness, then you can easily get the delta x. So find the distance of final image formed by the mirror, from the mirror. Object is placed at 21 centimeters. Radius of curvature is 20. Okay, that means focal length is kind of 10. Let's find out what is delta x here. Thickness is 3 centimeters. I'll put it here. Minus. They are saying refractive index is 3 by 2. That means it's kind of glass. It's definitely glass. 3 by 2. I'll put it here. So 1 upon mu will be 2 by 3. And it will be 3 centimeters into 1 by 3. 3 gets cancelled. So delta x is 1 centimeters. That means the normal shift produced by this particular glass slab will be 1 centimeters. It's going to shift the object by 1 centimeter. So what does it mean? It means that this is the object. So to the mirror, this ray which strikes appeals that this ray was coming from this point O dash, which is 1 centimeter forward, 1 centimeter in front than the original object. Now check here. What is this distance? O dash, if I subtract 1 centimeter from 21, it becomes 20 centimeters. And what is 20 centimeter? It's the radius of curvature, which means O dash is located at center of curvature. Very important problem. O dash is located at center of curvature, and I know the rays going from center of curvature come back along the same path. They retrace their path. So the ray which tends to, or it appears to come from O dash, will be going back, and if it goes back, it is definitely going back the same path through the glass slab also, and it is again going to land at O. So the final image will be formed at O itself. The answer will be then 21 centimeters. Okay, that easy. Next problem. They are saying we have a right angle prism ABC, and there is a little cross section BCD of, there is a glass slab of cross section BCD. The value of angle theta of the prism such that light ray incident normally on the face AB does not cross through the face BC. Okay. So if somebody is saying the light is falling and there is refractive index also, the light is not crossing, that means it's suffering TIR. Okay. And they are asking the value of theta for this, which doesn't happen. Okay, so I need to get the range, and they have given sine inverse 3 by 5 is 37, which we know. Okay, so in this diagram, what I'll do here, okay, the first medium is your prism, and its refractive index is 3 by 2, mu1. The second medium is refractive index 6 by 5, some refractive index. I need to write the critical angle for this medium, correct or not? How do we write the critical angle? Let's see. Sin theta c is 1 upon mu relative. Remember that. Relative means it's the reflective index of that particular medium in which you are located, the denser medium, with respect to the surrounding medium. Now see, if this light ray incidents like this, it's going to cross through the boundary of prism and strike the boundary of prism and glass slab. These are two different media. At this boundary, what I'll see, the glass slab and this prism, their refractive indices. So this is 1.5, this is 1.2, correct or not? So the glass slab is rarer and the prism is denser. Light ray going from denser to rarer can suffer TIR if the angle is greater than theta c. Which angle? The angle of incidence. So this angle, if it is greater than theta c, I am going to get TIR. So let's see. Mu relative I'll find is the refractive index of prism 3/2 with respect to refractive index of this glass slab 6/5, which goes in the numerator. So if I write it, the 2 goes in the numerator, becomes 4/5. So this becomes your sin theta c. I have got my theta c, and from that you can easily get ki the critical angle will be theta c. Now let's see, if the critical angle is theta c, what I can say about this angle of incidence. See here, the angle of prism here was theta 37 degrees, correct or not? No, sorry, they are asking you what's the angle. So let's say ki it is theta only, okay, some angle theta. This is 90, so what will be this angle of incidence? Angle of incidence will be 90 minus theta. Now what I need to write? I need to write ki this angle theta should be greater than equals to the theta c, right? It should be greater than theta c. So if it is greater than, sorry, it should be greater than theta c, otherwise it will pass through the face. So I should be greater than theta c. Theta c I found to be 53. Put it, it's 90 minus theta greater than theta c. Take the theta on other side and theta c on this side. So it becomes theta should be less than equals to 90 minus theta c. And 90 minus theta c will be what? 37. So theta should be less than equals to 37 degrees. If that is true, the angle of prism is like that, then it is definitely going to suffer TIR. Okay. Let's move on to the next problem. They are saying that object is placed at a distance of 15 centimeters from the convex lens, focal length 10 centimeters. On the other side of the lens, convex mirror is placed such that the image formed by the combination coincides with the object itself. Okay. Focal length of the mirror is. The object is placed at 15 centimeters from the convex lens and the focal length is 10 centimeters, focal length of the lens. On the other side, there is a convex mirror placed at its focus. Okay, so it's placed at 10 centimeters from here at its focus, 10 centimeters. And they are saying that the image is formed by the combination and it coincides with the object itself. The focal length of the convex mirror is. If I say that this was supposed to be the intermediate image, right or not? The ray starts from here. Let's first look in the forward direction, and it is located at some 15 centimeters, so it's going to form beyond 20 centimeters because it's between f and 2f, so image will be beyond 2f, so it will be more than 20 centimeters, something more than 20 centimeters. Okay, they are saying that the convex mirror is placed at the focus of this lens, that means it's placed at 10 centimeters. Wait. Now see, the image formed behind The mirror, or I can say this thing is, let's write the, whatever the image distance is, image distance minus 10 centimeters. Correct or not? So let's figure that thing out. For the lens, if I write the formula, then it will be 1 by v minus 1 by u is 1 by f. So 1 by v is 1 by f plus 1 by u. Focal length of the lens is 10, so 1 by 10, and the object distance is minus 15. Remember to keep the sign. So minus 15. Take the LCM, 30, and here it will be 3, and here it will be 2. So it's formed at 30. So V is formed at 30 from the lens. Now tell me, the mirror is already 10, that means this remaining distance V minus 10 is 20. So what I figure out here is the intermediate image is formed 20 centimeters behind this convex mirror. That means if the rays are reflecting back along the same line, this should be along the radius. Means ki the point of convergence, or where the intermediate image should have been converged, should be your center of curvature. So this distance must be equals to the radius of curvature. If that's true, if this is the center of curvature of your mirror, then the focal length will be 20 by 2, r by 2, which is 10 centimeters. So this is how we can answer based upon the situation. Let's move forward. So it came in your 2020 exam, September 5th, shift 1. Microscope, they are saying ki compound microscope consists of an objective lens of focal length 1 centimeters. FO is given here. They are saying ki eyepiece of focal length 5 centimeters is used, and the separation or the length of the tube is 10 centimeters. The distance between an object and the objective lens at which the strain on the eye is minimum, that means the image is formed at infinity with the minimum magnification. So the formula of total magnification, they are just saying ki the strain in the eyes is this, that's it. So the final image is formed at infinity, nothing else they are asking. Final image is formed at infinity. Okay. Alright, they are asking the distance from the objective lens, the distance of the object from the objective lens. So they have mentioned ki this is the problem of compound microscope, but I'll tell you ki it's just the problem of combination of lenses, nothing else. Correct? How is it? Let's see. If they would ask the magnifying power, then we could have written it will be minus V by U 1 upon FO upon FE, or FO upon FE, like this, D by FE. Okay. For the telescope it is FO upon FE, and for the microscope it is D upon F. I'll say ki here is the object and it is placed at some distance. Instead of U, I'll write X because we have to find it, X. Take. Focal length of this first is 1 centimeters. Focal length of this second lens, eyepiece, is 5 centimeters. These two are kept at a separation of 10. I'll make the image through this. It should be inverted first of all, correct? It should be magnified and inverted. If the final image is formed at infinity, that means for this lens, the object should be placed at its focus. Focus means 5 centimeters from here. So its intermediate image should have formed at 5 centimeters only. Why? Total length is 10. The distance from the eyepiece is 5. So the remaining distance from the objective is also 5. So what I can say, for first refraction, the image is formed at plus 5 centimeters. I know the focal length, I need to just find the object distance. So what I'll say now here, 1 by V 1 by u, 1 by f. So 1 by v is 5, and let's take the f on this side, and focal length is 1 itself. 1 by u is on the other side, and it is minus x. Remember, minus x means it's on that side only. So if you solve it, it will come out to be 1 minus 1 by 5 is minus 4 by 5, and that is minus x. So x comes out to be 5 by 4 in centimeters. Now they have said ki this answer of x, the magnitude we have got as 5 by 4 should be equals to n by 40. So you can cancel it, n comes out to be 5 into 10, 50. That's how you can answer the problems. Okay. So it was your J problem, and now you can easily understand ki if you can solve this, you can easily solve other problems as well. Okay. Let's move on to one problem of wave optics, your Young's double slit experiment. We'll go through some basic concepts of YDSC. They are saying in the YDSC, blue-green light of wavelength 500 nanometers is used. The slits are 1.2 millimeters apart. So lambda is given 500 nanometers. The distance between the slits small d is 1.2 millimeters, and the viewing screen is 5.4 meters away from the slits. That means the capital D distance is 5.4, which is quite large, as should be. They are asking the fringe width. So you must remember the fringe width. How do we find it? Is the distance between two consecutive maximas, the location of two consecutive maximas. So it comes out to be d lambda by small d. You just need to put it with proper signs. If I am finding beta, and here they have mentioned in meters, to convert everything to meters. So d is already in meters, lambda is in nanometers. So 500 nanometers means 10 to the power minus 9. Small d is 1.2 millimeters. So 1.2 millimeters means 10 to the power minus 3. Let's just simplify it. Minus 3 and minus 9, it will be minus 6. 2 zeros, so minus 4. And 5.4 divided by 1.2, as per the answer, it has to come and multiplied by 5. So it will come out to be 2.25 or 22.5 into 10 to the power minus 4. Okay, 5.4 into 5 upon 1.2 will be 22.5, and if it is minus 4, I can see that none of the options is 22.5, so I need to shift one decimal place. So I'll borrow one 0 here, and it will be 2.25 and 10 to the power minus 3. So that will be your answer in meters, which is the first option itself. Okay, the problem was basically remembering the formula of fringe width and what the fringe width implies. Alright, in YDSC, you need to focus about the locations of maxima and minima. For maxima and minima, remember that what happens. For the maxima, it's important that the interference happening is constructive interference, where the path difference should be integer multiples or the multiples of wavelength lambda, n lambda basically. Delta x is equals to n lambda. We say that the delta x is d sine theta, and then we proceed to write it as n lambda, and then we get the relation for the formation of fringes. Let's take another one. They are saying in this कि source emitting wavelength 480 nanometers and 600 nanometers is used in YDSC. Separation between the slits is 0.25 millimeters. The interference observed 1.5 meters away from the slits. Okay. The linear separation between the first maxima of the two wavelengths is. Okay. So what does this imply? The linear separation of the first maxima of the two wavelengths, that means you need to find the location of maxima of the first one corresponding to its lambda. So I'll write it will be general formula of maximas is n d lambda by d. For the first maxima, it will be n equals to 1. They are not asking central bright fringe, otherwise there would be no separation, correct or not? They are asking the first one. So n equals to 1. And if it is different lambda, then I'll put different lambda. Okay. So one of the wavelengths, lambda 1 here is 480 nanometers, and the other wavelength, lambda 2 here, is 600 nanometers. The separation between the slits, that means small d, is given as 0.25 millimeters. They are asking ki interference, they are saying interference is observed at 1.5 meters away. So capital D is 1.5 meters. And I think that we have gotten everything. So it's just the difference of these two, y2 minus y1. Okay. This is what they are asking, the separation between the first maximas of both the wavelengths. So I guess n d lambda by d will be same. So I'll keep d by d common, and then I'll write lambda 2 minus lambda 1. D is 1.5 meters and small d is 0.25 millimeters, that means 10 to the power minus 3. Lambda 2 is 600 and this is 480. So 600 minus 480 nanometers, that means 10 to the power minus 9. So it is, let's move it little bit on this side. D here is 0.25 and capital D was 1.5. Just writing it here. So 600 minus 480 is 120. So 1.5 into 120 into 0.25. Let's just simplify it. So this will be 6. If I take this 0.25 above, then 4 into 1.5 will be 6 into 120. Here it is 10 to the power minus 3, 10 to the power minus 3, and here it will be then minus 6 left. So into 10 to the power minus 6. Now 120 into 6 will be 720 into 10 to the power minus 6. And if I can see the options, the decimals are only different. Last one is not even correct as per the number itself. So what I'll do, I'll take the 10 to the power minus 6 here. So I'll write it as 0.720 into 10 to the power minus 3. Correct or not? And 10 to the power minus 3 is millimeters. So I guess one of our options is matching. 0.72 millimeters. Get the point? Alright. Now, this was about your wave optics. In this portion, if I say that the major proportion always is focused on your YDSC and optical instruments. Sometimes they ask problems regarding diffraction and polarization. So you guys need to keep revising the formulas of those topics. Okay. In the diffraction, we don't have much formulas. It's just that lambda by A format, the width of the slit width A. That's it. In the polarization, we should remember Malus law. In the Malus law, we discuss about the polarization, the axis of polarization, the angle between the axis of polarization, those things, the use of polarizer and analyzer, how the intensity changes upon. And also, if you know the polarization, then in the EM waves, the electromagnetic waves also, it is useful. As far as your ray optics or geometrical optics is concerned, in the geometrical optics, you need to revise the formulas, all the formulas of reflection, refraction, plane surface, curved surface, normal shift, the refraction through curved surface, the image formation, the focal length formula, the focal length and the magnification. You must remember the magnification formula and you should keep it handy. Okay. Means ki it should immediately pop up. You shouldn't be worried towards the actual formula, and never make a mistake in the sign convention. In the Optics, if I say, the most important thing you should always take care is sign convention. Never miss it out. What do we say for sign convention? The direction of incident ray is the reference direction. So it is always taken as positive. Is always taken as positive. For example, what does it mean? This was your concave mirror. If suppose the ray is coming from this side, it has to come from this side, cannot come behind the mirror. Okay. This direction is taken as positive. So if you are going to measure the distances from the pole, if I go towards the left, then I am going in the opposite sense. So these distances will be negative. If I go in the forward direction, virtual space behind the mirror is the virtual space, and in front of the mirror is the real space. So the virtual distances are positive. Above the principal axis distance we take positive, and below the principal axis distance we take negative. For the lenses, now for the object this is the real space, and for the image this is the real space for image. Okay, this is real for the object, while if the object distance is negative, I get real object. If the image distance is positive, I get real image. But here in case of mirrors, if both are negative, then we get the real object and the real image. A real object and real image. Okay, just be careful. What's the difference for the mirrors and for the lenses? Alright, so this was regarding your optics. I hope you liked today's session. Few selected problems we took. Just practice on more problems just like these, and all the best for your exams.